Okay, so let us start today's session. Jay, can you hear me? I can't hear you.
Yes, you are audible, but voice is a little bit slow.
Okay, just is it okay now?
Yeah. Speak some loudly. Some. Otherwise, okay.
Okay, is it better now?
Yeah, it's now better.
So let us start today's session then.
Yeah, we can start. Yeah.
So welcome all of you for week 7 live session for Advanced Research Trends in Smart Grid Technologies. I am Gagan Meena and I am doing electrical engineering in at IIT Bombay. So this will be the agenda for today's session. First of all, we will go through the overview of week 7 and then we will discuss some questions regarding that, and then you can ask your doubts. In between also, if you have any doubt, you can ask. Week 7 I think is more theoretical and so many facts are there, so the overview today will take a longer time than previous sessions. So just to remind you that the deadline for assignment 8 and 9 is March 22nd and 29th, so please submit the assignments on time. And you can find the recording for the live session at this link. It's also available in the problem solving tab on the portal. So let us start with the overview of week 7. In week 7 was, first of all, it was continuation of the operation and control of AC microgrids, where we discussed the hierarchical control. Then we moved to DC microgrid and then AC-DC hybrid microgrid. So in that we discussed different power management strategies in hybrid microgrid. We will first start with the hierarchical control in AC microgrids. So here we can see this is the main distribution network, which is taken care by operated by a distribution network operator, and it gives the reference signal is provided by this DLO. There are these 4 hierarchies. One is this global control, then central and emergency control, then secondary and local. So for each microgrid there are 3 levels of control, and then there is one global control which interacts with the distribution network operator and all the microgrids. So this one microgrid can receive signal from the other microgrids also via this global control. So there are these different microgrids, and this local control is at the device level. At the DG, for each DG, we'll be having one local control. Then, yes, Akshay, do you want to say something? Then above that is the secondary control, and then this is the central control. So we'll see in the subsequent slides with them individually. But the main thing is that the time of operation of these control is in this order. So this is the fastest. The local control will be fastest and this will be the slowest. For local control, we have decentralized control at local level, and in decentralized there are different types of control. And the most basic one is the root control, which is also there for the synchronous generators, the conventional generators. And because of some drawbacks of these root control, such as any small mismatch in grid impedance or change in the grid impedance parameters or estimation of these parameters, it results in an inefficient power sharing among the different DGs, which makes this control inefficient. Also, when there are single phase loads and non-linear loads, then also there is a problem because harmonic current sharing needs to be taken into account. And because of these reasons, different other types of troop controls are used. Then at secondary and central control, we can have both distributed or central. Any of these can be used. So depending upon our requirement, in distributed, these are the different types of techniques which are used. One is multi-agent, then model predictive control, and then consensus-based algorithms. The problem with the centralized is that there is only a single link, and if both of them requires communication. But so we can see here. Let us see this picture. So first see this. Global has only one. So global is centralized. This is totally decentralized, and secondary and central can have distributed or centralized. So we can see from this, we can understand these three controls from this picture. So this is the centralized control. So here we have a central controller which is having communication link with these three local controllers. And then these local controllers are having the physical connection with the respective DGs. So this green line represents the communication link and the black ones are the physical connections. So what will happen if there is a problem here? Then there will be disruption in power. So disruption in the control phenomena will be there. So that is why we move towards the distributed one, because it is more reliable. Even if one of the links goes out, still there are other links which can help in the control of the DGs. So based upon the reliability requirement, you can choose between distributed or centralized. Distributed is more commonly used, especially in DC microgrids, because it is reliable and also cost effective. So here this is a comparison between different types of controls. So here you can see global control. So global control, let us start with this local first. So local control for each DG will be having a local control. So it controls the output of DG in normal operation. In islanded operation, this central control will come into picture because it will detect. So this is also called the microgrid central control or MGCC. So in event of MGCC will be having this islanding detection techniques. Based upon that, it will decide whether the microgrid is islanded or not. This local control is totally decentralized because each DG is having its own control. Then the secondary control, it helps in power sharing for the parallel configuration of DGs. So if we think about the synchronous or conventional generators, then our conventional generators have their own governor action. So you can call it a local controller because each generator has its own governor action. But then at secondary control we can compare it to the AGC. So that is based upon the troop control. So how the power sharing will be there in event of frequency deviation. So it compensates for voltage and frequency deviation whenever there is a load variation or local control operation. And it can be centralized or distributed. Then the next level of control is the central control, which particularly it comes into picture when there is islanding. So it will detect the islanding, it carefully monitors the secondary and local controls based upon which it will decide whether there is a islanding or not. It will also help in the connection and disconnection of the grid to or from the main grid. And other emergency control and protection schemes are taken care by this central control or the MGCC. This can also be centralized or distributed. And above these, outside these microgrid is, so you can say these three are inside the microgrid. So within each microgrid we have these three controls, and outside the microgrid, for all the microgrids, we will be having one common global control. It will help in managing the power flow between different grids and between the grids and the main grid. So it facilitates the optimally economical operation of the entire system, entire distribution network. So we have already seen that it will receive the reference signals from the distribution management system or the DL, and this is completely centralized. So any doubt up to this point? And let us move ahead. So then we have different types of. So earlier we talked about AC microgrid control. So now let us move to DC microgrid control. So here also we have these three types: decentralized, distributed, and centralized. Just as in AC we had this troop control, here also we have the troop control, but it is slightly modified because of DC we don't have the frequency component. So the conventional truth characteristics are modified here. So here we have this BP characteristics. So different DGs can have these different characteristics which will determine the actual output. Here voltage, here power. So depending upon the slope, the droop is there. So this is delta V by delta P. So suppose if there is a 2% change in voltage, so power will change by this much. So in AC we have two characteristics, FP and PQ. So here, but in DC we have only this, because we don't have this Q and F in DC. This is for AC. Other techniques are this voltage leveling, DC bus signaling, and power line signaling. Similarly, for distributed also we have different techniques for DC microgrid. And then we have the centralized control. So just as in AC microgrid we have these two mode of operation. One is grid connected, another one is the islanded. Here also we have this in AC DC microgrid also we will have these two modes of operation, and we have the other mode of operation also. So can you tell which is the third mode of operation for any kind of microgrid? Apart from these two, grid connected and islanded mode, is there any other mode also? Jay, do you remember? Jay, do you remember?
Distributed, no? Third one is to be distributed.
No, we have these three modes. We have these three modes, right? Earlier in previous weeks also we studied that microgrid can have these two modes, grid connected. Either it can be connected to grid or it can be islanded. And there is one more. Is there any other mode also?
Islanded.
So in between them, so we have this one mode, right? Reconnection. When there is a transition from grid connected to islanded or islanded to grid connected, right?
Yes.
So that is also one. So we have these three modes.
That will be transient mode only, no?
Yes, that is transient, correct.
Transient mode.
That is transient. So we will see how different things changes during the transient modes.
Yeah. Correct, sir.
Till now, do you have any doubt?
No, clear.
And what about, so did you have any doubt when you were going through these lectures?
No, many things were similar. So like global control and centralized control. So there is a very thin line to differentiate again and again. Master control.
Global centralized is Same. Global is, we are saying it because entire distribution network is having only one country. So that is a level of, that is a hierarchy.
Yeah.
That hierarchy can have centralized control. It will always be centralized only. But suppose we are here, we are having this. So in each microgrid we are having 3 levels. One is this local level, then secondary level, and this third level, emergency control. So if we remove this, you can remove this control word. You can say local level, secondary level, and central level or emergency level.
Yeah.
So each of these can have different types of controls, but at local level we have only decentralized, because for each source we need one control. We want to control its output.
Yes.
Then these two levels can have 2 options. Either they can have distributed control or they can have a centralized control. So this level and control are 2 different things. So at these 2 levels we can have 2 options. Any of these can be used. This is the 4th level, which is outside the microgrid. This always has a centralized control, because it is receiving this information from this network operator directly.
Now, what is the benefit of secondary control? Either local or centralized emergency.
This
Central and emergency. What are the benefits?
Sometimes in some papers they only have these 3 controls. What you are saying: primary, secondary, and tertiary. And tertiary one is this global control is tertiary, and inside they have only 2. What you are saying, that they have merged these two, secondary and emergency control. So that can also be done.
That was my one doubt.
Yeah, we can combine them. Then the function which this was doing, the secondary has to do both the functions. But because of the islanding detection and the protection, these are 2 important functions. So we have this another level.
Okay.
Of control.
Yes.
Suppose if both of them are centralized, and in centralized the problem is that if this link breaks, then the control will not be possible. So if both are centralized and one of them, the link is out of service, then there will be a problem.
Yes. That's why. Yes.
So depending upon even the size of microgrid, different types of the generators inside the microgrid, all these things will determine the number of levels in the hierarchical control. So here we are having 4 levels. So in a smaller distribution network, we may work with only 3.
Yes.
That is possible. And the combined control will be inside one block. The combined function of these 2 blocks will be performed by a single block. That will be the difference. So as the number of level increases, the reliability increases.
Yes, definitely.
So that is why especially for big microgrids, big distribution network, we go for this 4 level control.
Yes.
Any other doubt?
Now, Please carry on. In between, we'll interrupt you.
Yes, sure. So we were here. So DC microgrid control. So when there are two modes, grid connected, islanded, and transient also we will see in this DC hybrid microgrid. For islanded we have two options. One is when there is only single microgrid. Second is when there are multiple microgrids. So in single microgrid here we are going for, we generally use this. Here we can use decentralized or centralized or distributed. We are going for decentralized. So here the DGs will operate in MPPT or off MPPT based upon the SOC of the storage. So Jay, did you understand this MPPT and off MPPT?
Should work in off MPT mode, no? Because it is islanded.
No, it is not because of islanding mode. So, what do we mean by off MPPT here? So here, since we are having only single microgrid, so we are using only decentralized control. We have only single entity to control. So this is the cheapest.
Power after islanding, power requirement of the microgrid will be limited. No? So
Yes, it will be, but loads are there, so we have to supply the loads. So suppose if, because in DC microgrid we need to have the storage for balancing the power load and generation mismatch. So if the SOC of the storage is below 90%, or even we can say much less, then MPPT, we can use MPPT. So we can extract maximum power from solar. But once SOC reaches at 90%, then we can go for off MPPT. That means we will not extract maximum power, we will just try to regulate the voltage.
so it will work in both mode depending upon conditions,
Yes.
load conditions.
So depending upon the storage,
Storage, the state of
charge of storage, it will depend upon that. Similarly for wind also. If we have wind and storage is not there, it is already fully charged, then by using the pitch control we can operate the wind in off MPPT mode.
Yes. Yeah.
So then in multi-microgrid we form they can be connected together to form a cluster, and this increases the reliability of the overall system and also better utilization of different DGs. So the next one is, why do we go for AC-DC hybrid microgrid? So can you tell?
The word hybrid means it will get the benefit of both.
Yes, so what is the benefit of both? What different benefits these two are providing?
So it will be a large network. Power flow will be easy. Control will be easy. These are all the things are. If you are working in a large network, having AC and DC both, so reactive power balance, load control, power flow, be easier. I think in the broader sense, I am telling. Broader sense.
Yes. So more important is that is true in one sense. More important is that the load. Just as we discussed in the last session also, that most of the load are DC, right? Lightning load, if we see. And other modern electronic devices, they are DC loads. And even if we have dominance of PV, fuel cell, even the storage, so all these are DC. Their output is DC. And right now we are having this only AC system. When we integrate these different components to AC system, then there are these different stages. Suppose generation is DC, then and load is also DC, but in between the system is AC. So we have to go for this DC, AC, DC conversion stage. So there will be multiple such conversion stages because of there are multiple sources, multiple loads. So as the number of stages increases, then conversion efficiency goes down.
Yeah. The drawback.
Yes. So this is the drawback. So one good option is to have this AC/DC hybrid microgrid. Here also, yes. So these are the main differences between these three types of microgrids. So in AC, the entire bus is AC, and we have to connect these different DC sources using these converters. So DC to AC, if this is AC bus. If it's already wind, then also we have AC, DC, AC stage. Then if we have loads here which are DC, then again AC to DC. Similarly, for DC, main bus is DC, and in AC/DC, there are both types of AC and DC buses. So these are the common stages of conversion in AC. DC to AC, then again DC. While in DC we have AC, DC, AC. Because this will be because of wind. We have wind. Output of wind is AC. But because the system is DC, we have to convert it into DC. Then again, if some loads are... Are you saying something?
Oh no. Somebody else maybe enter. No.
So then again we have to convert for AC loads. So purpose of all these connection is only one, that we want to access a deficient power should be shared economically, and we should be able to reliably meet the demand. So there are two types of structures in hybrid microgrids. So this is structure 1 and this is structure 2. So in structure 1 we have, so both these structures are interconnected by this interlinking converters. So here we can see this is DC bus, this is AC, so in between we have DC to AC bidirectional interlinking converters. Here also we have that in both the structures. And in structure 1 the difference is on both the sides, on DC sides as well as on AC sides, we can have different type of both DC and AC generation. So here we can see we have this DC generation, AC generation also. On AC side also AC generation, DC generation, and storage is there on both sides. So here also we can have AC DC load on both the sides. So here the problem is still we are having these multiple stages. Because on both sides, both type of source and load are present. Again, DC, AC, DC and AC, DC, AC stages are there. This is the AC. So AC generation is there. Then again DC, then again AC. This is for wind. This is for wind. This is done for this variation in for manipulating frequency. Because here we have this is variable frequency AC. We want a fixed frequency AC. So we have to do this AC DC AC conversion. And here also again this is DC, then again here DC AC. Here AC DC AC. DC AC again DC. So many stages are there. That is the disadvantage of this structure 1. But if we see the structure 2, then in structure 2 on the DC sides, only DC loads and DC sources are present, and battery and capacitor will also be there. And on AC sides, only AC source and AC load are present. So we can avoid these different stages. Correct?
Yes, correct. For structure 2, we will need lot of planning. Accordingly, we have to design.
You are correct.
Structure 1, it's not much planning is required. You can integrate as per generation, distributed generations.
That is why it is, this structure 1 is preferred when the major sources of power have both AC and DC.
AC, yeah.
Here we can have, if suppose AC is more, we can go for this type of configuration. But if we have a mixture of AC and DC, and then it may be difficult to geographically separate them. Right?
In case of renewable, mostly AC, DC, both generations are coming in a particular area, like some windmill, some solar, some battery storage.
So it may happen that because wind, we don't have wind everywhere. So let us say in Tamil Nadu where wind is more. So it may happen that there is a prominence of wind in a certain locality. And that can act as a AC microgrid. Hence, it is not always true, because we also will be having the storage. So if storage is here, then it's mixed. So this is much more practical, this AC/DC. For this we have to do a lot of planning. That is correct. Also, this requires optimal placement of all these different components. Then the last thing that was discussed was power management strategies in grid connected mode. So in grid connected mode, there are two different possibilities. Two strategies are possible. One is dispatchable power mode. So in this, what happens? The microgrid can act as both as a source or as a load. So it can give power and also accept power for charging the storage. Suppose this is the main grid, and here we have a microgrid, and if here the frequency goes above the nominal, so what microgrid can do, it can take power from the main grid and charge the storage. So frequency will go back to normal. Similarly, if the frequency is less than the nominal on the main here in the main grid, the microgrid can help it by supplying power. So in this way, it can act as a controllable source or load. That is why we call it dispatchable. And this is supporting the grid by providing voltage or frequency support. And we have in this dispatchable power mode, there are two types of mode, control mode possible. One is current control mode and another is the voltage control mode. In current control mode, so we are controlling the output of the output current. This is controlled to track the reference power. So this is a reference power.
Yeah. Bangalore must be Bangalore must have an
We are controlling this current. That is why it is called current control. And here the voltage and frequency are determined by the grid. So you can say this is a kind of PQ mode, or you can say grid feeding mode. Here we know the voltage and frequency by using the PLL, and we are supplying fixed P and Q by changing the current. Then the next is the voltage control mode, where instead of current we are controlling the voltage to regulate the power. This is similar to what conventional generators do. Then on the other hand, one is this undispatched mode, power mode. So here all the generator will only feed power into it. They will have NPTEL. They will try to inject maximum power by extracting maximum power from wind and solar and pushing it into the grid. And typically the storage is charged. So in this case, in both the cases, because in both the cases grid can supply the microgrid can supply power to the main grid. So grid support services can be provided in both the modes by controlling P and Q. But in dispatchable mode, one extra thing is that it can also act as a load. Then AC/DC hybrid microgrid. There are two types of modes. Grid connected. Same thing that we discussed here, just to see how these different components will behave. Because in microgrid we have this interlinking converters, DGs, as well as the storage, energy storage. And they can have different modes of operation based upon the mode of operation of the microgrid. So in the dispatched mode, in the grid connected mode, there are two types of possible mode of operation. One is the bus voltage control mode, where the interlinking capacitor will be controlling the DC voltage, and the DGs and storage on both AC and DC side will coordinate among each other so as to ensure power balancing between the different DGs. While this is first, but in the second we can have the interlinking converter. This is DC, this is AC. It is a bidirectional. It can operate in power control mode, so it will ensure this power balance. And the DGs and storage on the DC bus, they will control this DC voltage. So DGs here and the energy storage, they will operate in this voltage control mode, control the voltage on DC bus. And since because we are controlling voltage here, and this is operating in power control mode, so this will also operate in power control mode, AC side. So on AC side also, we will be operating on the power control mode. Then in undispatched case, the interlinking capacitor will operate in the voltage control mode and inject all the DC output into the grid. Because in undispatched, what we do operate these DGs in the MPPT mode. So we will extract the maximum output from wind and solar and feed it into the grid. So these DGs in both the side on AC and DC bus, they will operate in the MPPT control mode. And the storage are generally charged, but they can also be discharged for smoothing the output of these renewables. Because here DG and storage, so this is DC, AC, because these two on both the sides, they are just feeding power, so they are operating in power control mode, so but they are not taking care of the voltage, so this interlinking converter has to take care of the voltage in that case. That is why this AC link voltage is this is operating in the voltage control. Because we want to control both voltage and power. So this was a grid connected mode. Then we have the standalone mode or the isolated or islanded mode. Here also we have two types of control. One is the DC bus voltage control. In this case, the DG and storage on the DC bus voltage they can be, because it is working in standalone, so we have to maintain the voltage. So that is priority here. When it is connected to AC, any main grid, the voltage is provided by the grid. But here, since it is operating in the standalone mode, it has to generate its own reference voltage. So the voltage control mode is important here. So the DGs on the DC link voltage, they can control the voltage either directly or indirectly by loop control or power balance. Similarly, the AC voltage control on the AC side by the DGs and storage. And in both these modes, the interlinking converter can operate in any of these three, depending upon the control strategies. So, any doubt in this? Right now this is a little bit theoretical, but in the coming weeks there will be, I think, demonstration on these things, so it will be understood much better by seeing those results. Yes, Jay, are you saying something?
Yeah, what is the role of standalone ILCs in standalone mode? Both are operating in
because
what are the
yes. So actually this ILC is between DC and AC bus, right? Just go to this page. This is the main grid. This is the AC bus, this is the DC bus, and in between this we have this ILC. We are not having ILC here.
DC grid is standalone. What I mean,
yes.
DC grid is maintaining its own. DC grid is maintaining its own. Oh, what is the role of an ILC?
103.
Yes. So,
is any power flow taking place between AC to DC grid?
Yes.
In standalone mode?
Yes, it will happen because we are having what is happening in standalone mode. This main grid is not there. We are having generation on both the sides, generation as well as load. Storage is also there. So we have three things: load, generation as well as storage on both the sides. So
in grid connected mode, you discuss two cases: dispatch mode and dispatch mode.
Yes.
The similar scenario will come here also in standalone mode also.
No, because it will not come. Dispatched, what do we mean by dispatchable and non-undispatchable here is, it is in the sense that only when it is connected to the, suppose this is our microgrid. This entire is microgrid, okay, and this is the main grid. So dispatch is between this entire microgrid to main grid, like this, in bit to and fro from this main grid and microgrid, from this entire microgrid, combined DC and AC side.
Okay, that was confusion from my side. Okay.
So in standalone mode, it is not there. But load, generation, storage are still there on both the sides, and it is not that this summation of the storage, generation from storage, load, and these DGs on AC and DC side are equal. It may be unequal, and generally it will be unequal. So for that we have to do this balancing of load and generation, and for that this interlinking converter will be required. Suppose here load is more than generation, and here generation is more than load. So there will be a net flow of power from this side, correct? From AC to DC.
Yes.
And if the case is other way, load here generation is more on DC side, then the power flow will be from DC to AC side. So it may happen that and also it happens because suppose we have on DC side we have solar PV, and solar will be having its maximum generation during daytime, and on AC side if we have this wind is having its maximum generation generally in late evenings or night time. So their peak generation is at different times, and load is also the peak time of load, peak demand is also at different times. So there will always be a mismatch. So this interlinking converter will have to ensure this balance.
Yes, clear. Mostly it is a grid connected now. Standalone mode are, I think, very not common in India. Mostly they are connected to main grid.
Yes, standalone will be either when it is an isolated remote area is there, then it can be a standalone. Otherwise, only in some cases when fault is there or some such condition are there or blackout is there. So normally it will be grid connected, and there are abnormal situations, these microgrid can be islanded. If there is maintenance or fault, they can be islanded. There can be natural disturbances, then some microgrid can be islanded in that case. So, is it clear now?
Yes, it's clear now. Please go ahead.
So now that what you were talking about, the transient period, now we'll talk about that transient mode and also the loading conditions. So these power management strategies have to also ensure a smooth operation of this hybrid microgrid under these two scenarios, which is this transients, and there is a transition from standalone to grid connected mode, or from grid connected to standalone mode, or when there is a change in the load. Different types of loading conditions. So let us see first the transient operating mode. So in transient operating mode also, first one is this, when there is a transition from grid connected to a standalone mode. So in this case, we have also discussed in previous weeks different types of islanding detection techniques. Suppose before islanding, you can know DGs were operating in the we have grid feeding converter, so they are operating in the PQ mode of operation. And if there is an islanding, then it will. So before islanding, it was getting the V and F reference from the main grid. But now, when islanding is there, the main grid is no more. So it cannot operate in PQ mode. It has to operate in the voltage control mode. So it has to be grid farming. So some of the converter has to be grid farming. So we need, so either there are two possible scenarios, two things can be done. One is we change the control from PQ to VF or voltage control mode. Another is to have a uniform control mechanism for both the scenarios. It should be such that it works for both. So developing that is also challenging. So if you are able to do that, then also you can operate with this uniform control strategy also. So this will require power sharing among different DGs during the transition period. So that also has to be effectively ensured. And for this we need these islanding techniques, different types of islanding techniques that we have discussed. Do you remember, Jay, what are the different three, we talked about three types of islanding detection techniques.
Please repeat. There was some background disturbance from your side. I could not hear.
So, till what point did you hear?
Yeah. Just 1 minute.
Yeah, so I was asking, we discussed three types of islanding detection techniques. So, do you remember? Do you recall? What are those? I think 4 types. Yes, we discussed 4 types.
4 types.
So let me start with the first one. First was passive. Now do you recall?
So,
Passive islanding detection techniques. Third one was this hybrid. So hybrid is a hybrid of which two? Passive and other one was?
should be active.
Yes, it was active. So we had active. Then the other one was communication based.
Yeah, communication based first one.
So in active we were injecting some disturbances.
Yeah.
So in active we were continuously injecting disturbances. So in hybrid what we did, we injected only when after first we pass it through this stage passive. When it is detected, we will inject only when it is detected, so that we can improve the power quality. We can improve the power quality in case of hybrid. So now in standalone, second transition is standalone to grid connected. So in this also we need this change in control scheme. But apart from that, another important thing which is required in this case is voltage synchronization before reconnection, just as we do in case of conventional generators also. But there you can connect one generation or individual generator. But here in microgrid we have different types of generators, we have loads, we have even storage. So how to ensure the operation in such a way that the voltage at the kind of microgrid is similar to the main grid. So whenever we want to do the synchronization, we need that phase, frequency and voltage, these are all same. If not same, closed. They should be very close to the main grid. So these are the main grid parameters, and this is the microgrid. So for the synchronization, this should be almost equal. Otherwise there will be transients. And also they may not even synchronize. So we have to ensure this. So here we can have two types of synchronization. One is passive and another one is active. So passive, it assumes that voltage is very close and frequency differs only slightly. So it's an assumption. This doesn't happen in in practice, then synchronization may fail. So in this there is no guarantee of fast and controllable synchronization. And in this we do not require any islanding detection technique. But in active we can have fast and controlled synchronization of microgrid with the main grid. So here we can have these two different ways. First one is that one or more DG initiate the synchronization process and other will follow them. So this can be done with in microgrids which are having DGs with current control mode. But for the second one is when all the DGs participate in the synchronization. So this can be done for microgrids which are operating in the voltage control. But for both these, we need this communication facility. So different DGs must be able to communicate with each other for active synchronization. Then second one is this, apart from this transient operation, there are also different changes in the loading conditions which also affect the microgrid stability. So these constant power loads, they can cause instability in the microgrid because of their characteristics of negative impedance. And also in standalone mode, the frequency and voltage deviations are dependent on each other. So if some loads are there which have their dependence on both voltage and frequency, then also there can be instabilities. For example, we have induction motors. So they depend on both voltage and frequency. And if the deviation between V and F are dependent, then the normal operation of this induction motor will be affected, because in induction motor you have to maintain this V/F ratio. So if the deviations are such that this ratio is not able to be maintained, then there will be problem. So let us move to questions then. Is it okay? So what are the key control variables in a DC microgrid? NPTEL.
The voltage and current, the DC microgrid, key things.
Yes, key. Are you sure?
Yeah.
Are you sure?
Frequency ruled out,
Yes.
voltage and active. Yeah.
So this is also ruled out.
Yeah.
So do you know this, what type of group characteristics do we have for DC microgrid? Is it VI characteristics or something else?
No, it's not right.
It's a VP characteristics,
VP, yeah.
right? So it's in previous slide also we discussed, right? That
Yeah.
it can
So
operate
voltage and power.
either in voltage control mode or power control mode, right?
Power control.
So we want to control these two things in DC microgrid simultaneously in a, so they should be controlled.
And voltage and power.
So this is for now AC. Now for AC, what will be the option? Which one will be the correct option for AC? AC we talked about two characteristics.
Good.
What are the two characteristics?
Only you're talking only key control variables now. Otherwise,
Yes.
for all required active, reactive, voltage, frequency for AC grid.
Yes, correct. This is correct. So what are the two characteristics? Group characteristics that we use for AC microgrid. So for DC we have this VP.
VP
For AC,
for AC. Power will be there. I think power. Will be there. Power and frequency, I think.
Yes.
Should be.
So one is this FP. Another one is this
Q.
VQ.
VQ.
Okay. So this one also we discussed. We started our today's session with this hierarchical control. So which of the following is correct from top to bottom? So which one is the top control and which one is the bottom?
Top is global, then central, emergency, then secondary, then primary or local.
Correct.
Should be D.
Which one?
Global, central, then secondary, then primary or local.
Which one is the correct option?
Second one B.
B. This is from bottom to top.
Bottom to top. Okay. Question is from bottom to top. Okay. So the reverse order.
Which is
From local, then secondary, then central, and global.
so option
C.
C is correct.
Yes.
And then this, which of the following is true in case of conventional group control in a DC microgrid?
Conventional.
will happen in AC microgrid? What remains? What happens to frequency? Suppose AC we have this characteristics, right? F here or here. These are two different DCs. So what is constant here? Or if not constant, what we try to make constant? So we try to regulate this frequency constant. We try to make it within a band. And all the DJs, all the generation must operate at the same frequency. Correct? Correct?
So it is AC case, na?
This is for AC. So I was just making an analogy with the DC. So if this is happening in AC, what is happening in DC?
DC.
What will happen in DC? So in DC we want and also this is a reference.
Reference.
So in AC reference frequency this reference should not change, right?
It's constant.
Reference should remain constant.
Yeah, of course, reference.
Reference means that it has to. It is a reference. Right?
Yeah, reference means it should remain constant.
Yes. So,
See what is.
which one is the answer? This?
Yes, should be.
Yes.
Okay. Voltage only. Yeah.
Yes. Because in DC,
Right.
these are the two key parameters.
Yeah.
V and voltage and power. This is another question. This we have not discussed. Which of the following decentralized? Yes, you can tell. We have discussed this. So, which of the following decentralized control is limited to small renewable energy systems? So, we are talking about decentralized control here. And if we see option A, B, and D, they all are example of distributed control, not decentralized. For decentralized, we use only root control. Is it correct? To mention one thing. Should be DC micro. Then the option will change. This will be the option for DC micro. Voltage leveling. Next question is, in the hybrid energy storage, which of the following device helps to compensate for high frequency switching transient? Yes, Jay?
It's a good capacitor.
Which one? This one?
Yes, super capacitors. I think should be capacitors, not super capacitors.
Why not this super?
So,
This is
super capacitor are having low energy density. No?
yes,
Oh.
but here we are talking about high frequency switching transient. So here we require spike. We require power requirement is instantaneous power requirement is high. You want to, these are only transients are only short duration.
Yeah.
So we need high
Okay.
power density here. If we want a long distance,
High power. Yeah.
so if you
Yeah, super capacitor are having higher power density but low energy density.
yes,
With short duration, they will provide more power.
yes. So which one is correct?
No, super capacitor. In that logic, super capacitor.
That is battery has a, in comparison to supercapacitor, it has a low power density,
Is low power density.
high energy density.
Yeah, high energy density.
Capacitor is having
So,
very high power density,
yeah.
but low energy density,
Yeah, right.
very low in comparison to battery.
Yeah.
So in DC microgrids or transients, we use this supercapacitor.
Super capacitor.
That is why we have hybrid of this supercapacitor and as well as the battery storage. You can also have hybrid of supercapacitor and fuel cell. There is one vehicle which uses this supercapacitor and fuel cell hybrid. Because supercapacitor can cater to transients. For acceleration, initial acceleration, we can use this supercapacitor. And after that, fuel cell can be used. So this also we have discussed. So modern electronic loads, when they are connected to isolated AC microgrids, having PV as single source of energy, which conversion losses will be there? is also, these are the electronic loads. Load is AC or DC?
DC,
Yes.
but
Load is
grid
DC.
is AC.
But yes, grid is isolated AC microgrid. So grid is AC.
Grid is AC, load is DC.
So this is AC. This is AC. This is DC. So what will be that? PV is DC.
Yeah.
DC. This is also DC. But
Then first
what should
DC to AC, first loss will come DC to AC.
Correct. DC to AC. Then
DC to AC.
AC to AC.
Then AC to DC again.
Correct. So which one is correct?
AC to AC, AC to DC.
This is the option.
DC, AC, DC. DC, AC, then afterward DC.
B. So this is correct.
Yes, sir. Yeah. DC, AC, DC.
DC, AC, DC. Similarly, if we have a wind, we have a motor load connected to
Motor load.
DC microgrid and having wind as the source. So here we have wind. We have wind.
AC, DC, AC.
So this is our motor load. Motor is taking AC input. We have DC microgrid and output is AC from wind. So correct. AC, DC, AC.
Yes. AC, DC, AC.
Correct. Yes, now we have to discuss, we discussed this role of interlinking converters, DGs and storage in case of grid connected undispatched power mode of hybrid microgrid. So which one operates in which mode? That we have to answer. This is the undispatched mode. So in undispatched mode, we extract maximum from solar and wind. Maximum power from DGs and feed it to the grid. So DGs will operate in MPPT or off MPPT. want to extract maximum power from solar and wind. So all the solar and wind DGs have to be operated in the maximum power point mode. Here is solar. Here we have wind. This is interlinking converter. Because we are setting maximum. Power here to the main grid. So this converter has to regulate the DC bus voltage.
Option B should be there.
So storage can
ILC
charge.
will regulate DC voltage. Easy in
So in 2, everything is same. Only this last option is different.
always okay. No. Charging, discharging, both will take place.
Yes, both are possible.
It's both, yes, both possibility are.
Storage can
See, correct.
charge also for
See,
smoothing the output of renewables. It can
Yes.
discharge.
the correct option is C.
Also, because we are generating maximum, so the excess generation can be stored in the storage, and then the rest can be sent to the main grid.
Yes.
This also we discussed at the end, and because what is the impact of loading conditions. There are these two modes, one is grid connected island net, then there are transients, transition mode, then there are some problems due to loading conditions. So this is a question on that. So which of the following type of loads can cause instability issues under loading conditions? This they have this negative impedance characteristics. CPLs, constant power loops. They can cause instabilities in the microgrid. Then we have global hierarchical control is which one? So this we discussed, right? The global level
Is centralized.
control has to be
Yes. Centralized level only. No? Global is some type.
yes. It has to be centralized. It is always centralized. But
It's centralized.
what if I say central? Then
Central.
this is for global, right?
Yeah.
So which one do we use for decentralized? Decentralized is for which level?
Decentralized local. No? It's
Yes.
for local. Yes, for local. Local. Yeah.
So this is centralized, and this is your decentralized.
Yes.
Then what about these two? Distributed or centralized? Can we use both? Which one of these?
What is the question now? Please repeat.
So here now instead of global it is secondary or central. Secondary or central.
Yeah.
Then which option will be correct here?
Secondary distributed and secondary distributed control. Secondary is distributed control.
Distributed or centralized also we can. It's both of either of the two can be.
Yeah. Either of it. Yes. Distributed or
Centralized.
Centralized. Yes.
So now is it clear which level will be having what type of control? Right? Is it clear now?
Yes. Clear. Yes.
Yes. For global it is centralized.
Yes.
Poor voltage regulation in droop control DC microgrids is due to. Suppose if we have these two curves, let me change the color. So this is DG1 and this is for DG2. Okay. And
Your word will due to large group quantities.
yes, why do you say so?
Due to large group quantities.
Yes, that is correct because you can see here. Suppose this is voltage V1 and this is V2. So we can say this is before disturbance, this is after disturbance.
Disturbances.
And we were operating on this. This was the P for DG1. And this is for 1 and this is for 2. So we can see here. This is actually for, I have to change. I think This is for same voltage loop. For both the characteristics, same voltage loop, same voltage regulation is there. Then Dg2 will have lower change in P. If we do it other way, change in P is same, then what will be the voltage regulation for both? This is the change in P. This is P1, this is P2. So if we see this curve, this is voltage regulation. But if we see this curve, then it is here. It is here, correct? This is the voltage regulation. Correct?
Yes.
So large droop, this is having droop, the droop for this is more. So large droop will cross large. So poor voltage regulation. Correct?
Yes, correct.
Now next is, which of the following entities are responsible to maintain DC voltage in grid connected DC microgrids?
It connected DC.
So who will maintain this voltage? Bus voltage.
The voltage source converter interlinking DC utility.
Correct.
That is grid connected.
Correct. This is correct. So this has to be done by the voltage source converter.
Yes.
Because in grid connected mode, this will be supplying power.
Yes.
They will be operating in MPPT or off MPPT. Voltage will be maintained by this. An islanded hybrid AC-DC microgrid has excess renewable and fully charged storage, feeding uncontrolled load. Both in AC and DC, possible solution to maintain the system stability is. So storage is fully charged.
Storage is fully charged and isolated, islanded.
And there is an excess generation.
The generation fully charged storage.
So we cannot charge storage more. And also it is islanded, so we cannot even supply it to grid. storage also loads are uncontrollable. So we don't have storage, we have only loads, and we have this DG. The sum of generation should be equal to this P load DC plus P load AC. So this power has to continuously change to meet the load. So we will be using DG in this mode. Yes. Storage is already charged, so we cannot charge. Generation is already more than load, so why to go? Load shedding is not required.
Not required, yes.
It will be there only if generation was this. So since storage is fully charged, generation is also excess, so we have big changes. Do you want to say something?
No, some disturbance is coming.
Yes, so it will operate in this power dispatch mode.
Power disturbance, yes.
Yes. This was the last question. So this also you can go through this if you want. These are I have taken this from some paper. These are more. This is another elaborate classification of different techniques for AC, DC, and hybrid. So we have seen this one in lectures, phase angle group, and virtual impedance, and virtual power transformation also. Then one was also virtual inertia based. Traditional also we have seen. This we talked about in distributed approach. We talked about these three techniques: multi-agent, model predictive approach, and consensus theory. So these are additional, just for your knowledge. You can, if you want to go through them, you can read inductive voltage group. Then synchronized Q-based mitigation technique. This is primary, secondary, and tertiary controls. These are the intelligent approach. This also we have seen in the lecture. Intelligent techniques, fuzzy logic, neural network, wavelet, ENFIS also. This is new, proportion resonant approach. DC bus signaling we have seen for DC. Also, we have seen that power line signaling, and voltage leveling, and root control. And this is also there. These are some additional techniques which can also be used. And one is this mode adaptive MADA. For hybrid, these are some new techniques: evolutionary based, synchronized control, role of hybrid system and intelligent coordinated systems approach. So if you want, you can go through them. Any other doubt? So is it clear? Everything is clear, yeah? So when we will see those implementation of these different techniques, control, and also from the next week, not to next week, from 9th week onwards, demonstration of different techniques will start. So how these control are exercised in practice, what are the different blocks, that we will see in the week from week 10 onwards. In week 9 also there will be discussion on how this NPTEL algorithm is implemented in both solar and wind. Next week there will be some discussion on cyber security, grid resilience. So these topics will be discussed in the subsequent weeks. So once again, just you can go through these lectures or these slides also, because these are even more condensed version of the PPTs available online. Still, if you have any doubt, you can ask in the next class also, next session. Is it okay, Jay?
Yes, okay. Just quite exhausted.
Yes.
Yeah.
This week was very more theoretical. So many facts were told, but how they are actually implemented, what is the actual control, how to implement these different control strategies, that is another step. That will be cleared in the demonstration classes, as sessions.
Yes, sir. That will be more practical.
Yes.
To understand the things. Yeah.
Implement those in laboratory.
Yeah. Yes.
That we will see from week 10 onwards. 10, 11. Even in 9 you can see how to implement this MPPT. We keep on saying that we have to extract maximum power from solar, but how do we actually do it? What are the different algorithms, how do we implement that? We will see in next week.
Okay.
Then let us close then.
Yeah, now close.
Next Tuesday, same time.
Yeah.
Hopefully next session will be
thank
more
you.
interesting. Today was it was not that interesting, I think.
No, it was interesting. Actually, one has to revise again and again. A lot of concepts are mixing type things.
Especially in
So
today's
you have to
session,
read.
lot of information, especially new.
Yeah.
Everything was new, and so
Yeah.
much information was bombarded. So
So
it will take time.
no, For that you have to come prepared to listen also. Viewing the previous lecture, listening again, then things will be more easier. It's okay. A lot of concepts are clear.
Okay, so that is next Tuesday. Thank you for joining.
Yeah. Thank you. Very good session. Thank you. So close now. Thank you. Taken a lot of efforts. Thank you.